it's important to talk about control objectives. Usually, about 2/3 of the time, it turns out, the control objective is to keep the controlled variable as close to set point as is practical. Not necessarily as close as possible, but as close as is practical. That's the case with cruise control. Generally speaking, the cruise control is trying to keep the speed as close to set point as is practical. Now, there is a compromise in there in that the cruise control is not going to use infinite control action in the event of a small control error, but nevertheless, it's trying to keep as close to the set point as it can. Some of the time, the control objective is intentionally slower than that. Now, we'll get into reasons for that later on in the course, but suffice it to say that sometimes you actually want to be more careful with your controller output because that may have other impacts elsewhere in the process, and you may not want it to change really quickly. So the most useful control design question anyone can ask is, how fast do you want the controller to get the process to set point? Now that requires us to come up with some definitions in order to be able to answer that question directly, and that's what we'll be doing next. So another definition, servo control. Many people have heard of servo motors. Some people may even know what they are. But servo within the control community refers to when you are changing the set point or desired value from one value to another, and you want the controlled variable to move along. So let's say you're starting with, in a city, you're driving along at 60 kilometers per hour, and then at 12:05 p.m. you encounter a change in speed limit from 60 to 80 because you've reached the edge of the city, and so the speed limit increases to 80 kilometers per hour, and then you can proceed along at 80 kilometers an hour. So it would be possible or it's a worthwhile thought experiment to consider how we would actually achieve this. So at 12:05 p.m. as we go from 60 to 80, if we want to instantaneously get from 60 to 80 kilometers an hour, that would take infinite throttle position, infinite input to the engine, infinite torque, infinite power output, and then immediately thereafter the throttle position would return to whatever the steady state throttle position will be at 80 kilometers an hour. Now, no one's going to suggest that that's the right thing to do, but it's a worthwhile boundary, our edge point for our discussion. So what's another boundary? Well, another boundary is if we're driving along and then we reach the point where the speed limit changes, I'm going to use a different color now, I'll use black, we could just change the throttle position to what we know is going to be appropriate for the new speed limit and just leave it there. And give or take my hand shaking, we get a straight line. So what will happen to the speed? Well, what happens to the speed is that it will increase in some asymptotic manner that, depending on how powerful your car is, will take a greater or lesser time, but it will eventually reach the set point. It will not get there immediately. It will get there, eventually. Okay, so these are really the two meaningful extremes for control. Infinite control effort giving you immediate response, and steady state control effort which gets you there sort of asymptotically eventually. Well, what are we really interested in? What we're really interested in is some sort of response that gets us there in a reasonable time, without annoying traffic, other drivers too much, and gets us there pretty quickly. Well, what would the control effort look like for that? It would probably be a pretty big sudden increase, you'd put your foot down on the gas, and then as the car accelerates, comes up to speed, you would then drop back down to the steady state value. Okay, so we now have the notion of slow and fast servo response. Let's talk about how we would actually quantify this. Now it turns out that here we have a curve for a typical servo control response, and there's three standard measures that we use. And the first one is not necessarily, no one of them is perfect. The first one, the most obvious one, is how long it takes from the time the set point changed until the first time the controlled variable is equal to the set point. And that time duration here we call rise time. Now, as you can see, in this case, we got a relatively short rise time, but we got a considerable amount of overshoot. Sometimes that's okay, sometimes it isn't, but it's certainly worth quantifying. And the way we quantify the overshoot is by taking the ratio of how far we overshot, call that A, divided by the change in set point, let's call that B, so overshoot is equal to A divided by B, and it's typically expressed in percent. So here the change in set point was 1 unit. The maximum value it reached was about 1.16. So the overshoot here is about equal to 16%. Now, whether that's good or bad depends entirely on what your control objective is, but 16% on the face of it looks pretty reasonable. Now, the third and probably most important measure of servo control performance has to do with how long it takes for the set point for the controlled variable to get to set point and stay there. Now, mathematically, the controlled variable approaches the set point asymptotically, so it's never exactly the same. But more importantly, it's unrealistic to expect there to be no disturbances, no values that push the controlled variable off set point forever or until it quiets down. So what we do instead is we take a pragmatic approach and we define a tolerance band either side of the set point. And this tolerance band is defined as plus and minus 5% of the change in set point. And what we do is we find the time when the controlled variable went into this tolerance band and then stayed there. So not this first time where it shot through, but at this point here where it went into the tolerance band and remained in there for the rest of the time. So this time here, from the change in set point to this time here, somewhere around 30, this is called settling time. So rise time tells us about the initial response, overshoot tells us about overshoot, and settling time tells us how long it took to actually get to and stay at set point. Those are the three standard important measures of servo control performance.